energy. You've probably heard it before. You've probably even heard what the definition is: the ability to do work. There's a bunch of different types of energy out there. And it's everywhere. Everything's got energy. There's energy that comes from gravity. There's electromagnetic energy that comes from electricity, obviously, and sunlight. Sunlight has energy in it. Chemical energy, the energy from chemicals interacting, thermal energy, the energy from heat, the mechanical energy, the energy that machines can do to turn and move, nuclear energy, the energy and ionization energy, the energy that's inside atoms that we can break apart and utilize. There's even energy from sound, the sound waves that are coming out of your screen or out of your speakers and into your ears or out of your earbuds in your ears. That's a form of energy. It's getting to you through energy. So, there's two major categories of energy. There's kinetic energy and potential energy, which you've probably heard before as well. Kinetic energy, the energy of movement. Potential energy, energy that can be used for something else. Two different forms. But really, we might have heard many of these before, and we might have heard a ton of them before, and you might even be well versed in this. But really, when it comes down to it, what is energy? Really, what is it? I mean, like, for example, take this piece of wood that I got from Prince William Forest Park. By the way, it's shameless plug. They're open right now, and they're open for free with no admission cost. I highly recommend going. It's good for your health, and also the coronavirus doesn't like sunlight. So go to the forest. It's amazing. But anyway, I got this piece of wood, and you can do a lot of things with it. I mean, for example, you could burn it, and burning it would give heat. So it looks like there's some potential energy in here, right? That I could burn it and get heat out of it. So there's energy in here, but what is that energy? Is it like does the wood have like, I don't know, like energy particles inside of it? Is it like wrapping its arms around particles of energy, or is it like something else? Where is the energy? Well, it's nowhere and everywhere. Energy is a property, or really a state of being. It's not really an action. So this wood has energy in it because it is wood. And wood, because you always know, it always has energy. If it didn't have energy, it wouldn't be wood. If you couldn't burn it, it wouldn't be wood. And so it's always got this potential energy in it because it's wood. How to get that energy, you think? Well, I started thinking about that, and I started thinking, well, trees, right? Yeah, if you go to a tree and see, it puts a lot of energy into making wood. And so use all the energy to generate a substance, a physical substance that is by its very nature chock full of energy. That's why you can burn it and get energy out of it, because a tree put energy into it. And that really gets us to the major idea of one of the most fundamental properties of energy. Is the fact that energy always is constant in the universe. It never increases in the universe, never decreases in the universe. You always have the same amount of energy. It's always there. No matter, I mean, you might lose energy from doing important things and doing important work, but that energy is still in the universe. You could transfer energy into your keyboard as you tap keys down. You release energy as you release heat from your body, but it is all just energy. The energy is always going to be there in some way, shape, or form or other. So it's really important to remember that the amount of energy in the universe, it's always the same. A tree puts energy into wood to make wood. We burn the wood and get energy in the form of heat out of it to warm our home or just to have a good time. And the energy will always be constant in the universe. It'll never change. It's just converted from one form to another. So that brings us back to two different types of energies. There's kinetic energy, which is a form of motion, and it's just anything that moves. And there's potential energy, which is just all other kinds of energies. So, for example, if I were to take a book, let's say I took a book, and I dropped this book, right? Okay. Boom, I dropped the book. right? And you think what I just did here is I just converted this energy from kinetic, from potential. It's potential energy. It's raised up. It's at a certain height, and so it can fall down and has the ability to do work. And so it has this potential energy, and then it falls, being energy, being kinetic energy. So immediately, in an instant, I convert all of this potential energy into kinetic as it falls. So it falls and falls and falls. So I just made a conversion from potential to kinetic just by releasing my hand. So that's pretty cool. You can convert energy really easily. And then it hits the ground. So it was first potential energy, then it went to kinetic energy, and now the book's on the ground. So I guess the energy is gone then, right? Not at all. The energy is still there. Well, it's outside the book now. It's gone from the book. But now it's actually in the ground. It's actually in the ground here. It's instead of just being in the book, the book sent shock waves into the ground, and the ground shook, and shaking created friction. The friction created heat, and that's kind of confusing. Maybe here's a better example. Let me hold on for a second. I'm gonna move you for just a second here, if I can. I don't think I can. Oh my! Let's see if we can try this. So, got a bowl here, and in this bowl, we have water. Just absolutely nothing but water. So let's say if I try to drop a piece, just a little object into this water and see what happens. It does what you expect it to do. It creates little shock waves or little ripples that go throughout the water, right? So what's happening there? If I create these shock waves, oops, sorry, that's a lot of movement. I hope that came through. When I create these shock waves of water, what happens is that the potential energy of dropping the little, round to it into the water creates waves of kinetic energy. So the water receives the energy from the object, and then turns that into kinetic energy, starts moving that and using that and all that stuff. And then as these waves start moving around and going all over the place, eventually they kind of dissipate a bit. And after they're dissipated and molecule starts bouncing around enough, eventually it just kind of gets, from friction, kind of just converts into heat and is done. It is now in heat energy. All I'm saying is, from dropping this object, it created so much movement in the water and friction in the water that it heated up the water just the tiniest bit. And the same thing's happening when you drop a book, or anything else for that matter. When you drop something, it creates a little shock wave, a sound. There's some sound energy that comes out that you can probably hear. There's a little bit of movement that creates some friction and creates some heat. And so those are the kinds of energy it gets converted into. And here's something else that's interesting about that energy. Let's say I have two books, and I want to drop both those books. I think this is really cool. So, hold on. I'll let you take a second and point that in your mind, because this is first off, this is really cool. The fact that when I drop this book, the energy is still there. It's just now in the ground and in sound and in heat and all of those other things. It does a bunch of conversions in a few seconds, from potential to kinetic to sound. So we've got that. And now, let's try something different. Let's say we took two books. Let's say they're about the same book, they're the same size. For simplicity's sake, let's say they are the same size, they're the same book. This book has some potential energy. This book has also some potential energy. But if I raise this book up, we would say this second book, or I guess your first book, the second book, has greater potential energy. It has more potential energy in it, whereas this book has less potential energy. But when you really think about it, the question is, well, what's the difference between these two books? In some ways, well, they're still the same book. They're the exact same book. They're the same book, and they're composed of the same molecules. They have the same matter. They have the same everything. But when I raise one up, this one has more potential energy in it. So it seems to show then that, well, maybe potential energy isn't really a property of the book, as in it possesses some energy, or it possesses molecules or anything like that. It's just, it's a state of being of the object itself. These books are identical. These books are exactly identical, but when I raise this book up, this book has more potential energy, even though it's the same as this book. They're the same book, but but the energy is different. That's the way to think about it. That energy is now, it's the kind of the property of it. It's a state of being. It's not really something that affects the object itself, the molecules of the object itself. For the most part, there's exceptions. There's lots of exceptions, but the general idea is that energy is a state of being. It's a property. Okay. So we've gone through a lot of those things. We've covered a lot of ground already. I want to give you just a couple more examples of what energy can look like. Here's one. Let's say I wanted to use this Sawzall. It's my weapon of choice in the zombie apocalypse. I know most people like guns. I'll go down and I'll die, but this will be fun. So I think it's a lot more fun than anything. So or any other weapon. So we take this Sawzall and you'll notice, before I even do anything, you'll notice that it has a really, really thin blade on it. And that's what blades are. They're just really, really, really thin surfaces, extremely thin surfaces. So if I take the entire weight of this Sawzall and I put it on top of a piece of wood and then turn it on and let it go, that really, really, all that gravitational energy and all of this kinetic energy from this blade, as it moves back and forth and back and forth and back and forth to saw into this piece of wood, that gravitational energy and that really, really, really concentrated kinetic energy will be enough energy on just a tiny spot to actually split the block open. It'll crack, it'll sever molecules, or sever the bond between different molecules to make a separation. So in some ways, that's another way of transferring energy. It creates heat. It creates such amount of heat right on that spot, heat energy, that actually severs bonds. So that's another form of energy. And even another form of energy, maybe something that's an electromagnetic form of energy, would be through circuit boards, or even just a circuit if you were to build one at home. If you were to like set up a light with a battery and an LED or something. As electricity goes through the circuit board, it's a clean circuit. Energy is conserved. It goes in, it comes out. You put energy in, you get energy out. And even with batteries, when you plug a battery onto a circuit board, electricity goes through one end, and electricity comes out the other end. It goes back into the battery in the negative terminal where it's unusable. So energy in a circuit board is always conserved. Now there's some transfers of energy too. This will convert to heat energy, and this will convert a lot of heat energy, because there's a lot of really minute circuits in here, and it can get really, really hot. So this will make a lot of heat. So when you feel your computer heating up, that's because energy is going through it. Electromagnetic energy is going through it and creating a lot of friction, in a manner of speaking, and causing heat energy to form. So energy transfers, that's happening all the time as you listen to this. Okay, so that's a lot we've covered. A couple more things that I think that'd be really helpful to know. And again, these will all be notes that will be posted later. But I just want to kind of introduce you to these ideas and really get you, to taste and see how cool these things are. So the next one is mass. Mass is really important in energy. So let's say I took the mass of lifting this book. This is one book. It takes a certain amount of energy to lift this book up, right? Yeah, it takes a certain amount of energy. I've lifted this book up a certain height. That's some potential energy. There's a lot of potential energy in this book. Now let's say I didn't just take that book, but I took all these books and raised all these books up. Well, now I've created a lot more potential energy. The only difference is I just changed the mass. There's more mass now of book, and so there's a lot more potential energy when I raise it up to the same height. So if I was to drop these books, it would create a much greater thud, because there's so much more energy. All I'd say, mass is really important. The amount of mass that's in it helps determine how much energy is there. So if there's, in potential energy, if you have more mass, there's more energy. So we use that in batteries, in batteries all the time. They're trying to think of how to make modern batteries with water. And so one of the things they're thinking of is, let's try lifting up a bunch of water way high up in the sky, like a water tower height, but like entire lakes. Let's lift entire lakes up into the sky. And then after we've done that, or maybe up on a hill, and when we've done that, whenever we need energy, we can just let water flow down the hill, and have some turbines to collect energy from it. And these turbines will spin, and they'll be generators that create energy. So that's one of the ways we're thinking of how to like solve the big old problem. If you've heard, there's a big problem with like solar panels and wind turbines and all of those, because it's like we can make energy, but with a solar panel you can only make energy during the day, and a lot of people watch TV at night. Like, how do you give them energy if you're living off solar panels at night? And so it said we need to find a way to make a really nice battery, and that's one of the solutions. It's a cheap battery too, so it could, with enough water, you could serve an entire city. Same thing with windmills. Wind only blows so often, and it's not always blowing. So if you need electricity and the wind's not blowing, how do you do it? Well, you create batteries, and one way to make a battery is just with potential energy. You raise things up into the sky, and now there's a lot of energy you've stored. Whenever you need the energy, you just let things fall back down to the ground and collect the energy as it comes back down. It's cool stuff. Okay, all I'd say, mass is important. And mass is important in kinetic energy as well. So let's say I want to take a book. Let's take a big, hefty book, or a decent book. Let's say The Growth Mindset by Coach. And let's say I wanted to see how much kinetic energy is in this book when I push it. I've got a really great device to measure how much kinetic energy is in a book. In fact, it turns kinetic energy into sound energy, or sonar energy. It's called my door. So, so here's what I do. I want to slide this book to the door. And you can probably imagine what will happen. If I slide it with a reasonable speed, but not a really incredible speed, it'll hit the door and make a decent, satisfying thunk. That's what we expect. Now, if I were to take that same book, though, and I was to slide it towards my door at twice the velocity, at twice the speed, well, you'd probably think it would hit the door twice as fast. Let's see what happens when I do that. It makes a bigger sound. It makes twice the sound. So this device, called my door, is measuring the amount of momentum in that book. The book is, when it has less momentum, it creates a slower sound. When it has a greater momentum, it has a greater sound. And what I'm trying to say here is or kinetic energy, when it has less momentum, this momentum and the kinetic energy are the same thing. So when I take this book and I slide it to the door, and it hits the door, and it has less kinetic energy, then it makes a slower sound, it makes a quieter sound. But if it has more kinetic energy, it makes a larger sound. And what we notice is if I take a book and spin it with twice as fast, it'll make twice the sound, make twice the volume. So that means velocity is important. The speed of something is moving determines how much energy is in it. In other words, if I push this book twice as fast, it's going to have twice as much energy inside of it. Okay. Or it's going to be composed twice as much energy. Not energy particles per se, but its state of being will be twice as much in energy. Okay. So that's one thing. Velocity is important. Twice the velocity, twice the energy. That makes sense. Twice the kinetic energy. What happens if we change the mass? Let's take that whole stack of books now, and see what happens when we take the whole stack of books and try to push it towards the door at the same speed. what do you think will happen? If I push it towards the door and it hits the door, well, it should hit the door, and if with all this mass, if it is the same mass as one book, well, if it has the same amount of energy as one book, it should make the same sound. If it has more energy than just one book going at that speed, then it should make more sound. Let's try it out. That was more sound. If you did not notice. So there was a lot more sound there, which means that the more mass I had, the more energy was there. Many books creates more energy. So more mass is more energy, more velocity is more kinetic energy. So what this really boils down to is an equation. This will be in the notes. Is that momentum or kinetic energy is the same thing as mass, the amount of mass you have, times the velocity. So if you have twice the velocity, you have twice the kinetic energy. If you have twice the momentum, you have twice the kinetic energy. That's what we're trying to get at here. All right. A lot of really cool things. I think I've had a lot of fun here. Let's talk about one more thing. Total energy. The total energy in the universe. When I was young, I heard about this idea of the law of conservation of energy, about how energy is neither created nor destroyed. There's always a constant amount of energy. And I thought, I wonder how much energy is in the world. Because you think I could burn this piece of wood and get a lot of energy out of that, a lot of heat energy out of that. We could drop everything that's in the sky down to earth, and that we get a lot of energy out of that. And you can just do so much stuff. And you can do all these chemical reactions, get a lot of energy out of that, and everything eventually may be able to be converted into just pure heat, almost, nearly. And so the question is, like, how much energy is there? I thought for so long, until just today, until I started researching it, I sort of thought, oh, maybe it's like 10 to the 500,000th newtons. It's just like an incredible amount of energy. We're talking the whole universe here. So Stephen Hawking did some research into this, and in his really important Theory of Everything book, he actually proposed an idea as to how much energy is in the universe. His idea, get this, a net total energy of zero. Zero, right? How? How is there zero? There should always be energy. Are he saying this is no energy? Yeah, he's saying this is no energy. So here's what he's saying. When you raise a book up, that's positive energy. You got to put a lot of effort in to get energy away. You put a lot of energy in to get it away from the ground. So you're putting in positive energy. When you drop the book, it gives you back energy. So you're putting in negative energy. So you put in positive energy, you're putting in negative energy, and you get energy back. So, in other words, the total amount, after putting in the energy up and getting energy back, the total energy that was involved here, that the book went through, is a net of zero. It got some, it lost some. So it's nets at zero. So that's just what gravity does. You create energy, you lose energy. In other words, this works the same thing with matter. You create matter, you get antimatter too. Except, for some reason, at the beginning of the universe, somehow more matter, who knows why, more matter got generated than antimatter. And I'm simplifying here. And physicists are still puzzled as to why that could be. Something else they don't understand is why the universe would even do any of this. Why? So there's a net of zero, but why would there be any fluctuations at all? Why did if the book goes up and the book falls down, that might be a net energy of zero. But why did the book go up in the first place? Why is there that fluctuation? I mean, in a perfect universe, there would be no net energy. There would be nothing, just like a homeostasis of heat and maybe some matter dispersed around or something like that. But there's no energy. Why is there all this movement? How did this separation happen to create all this? Who does that? And the more I get into physics, the more I look into these things and people we get, the more I see it really is a God-sized hole in all of this. The only way we can explain why all this happens is God. And I think the beauty of it is that everything follows this rule of thermodynamics. That the only reason why we can do anything is and be here at all is because someone broke the first law of thermodynamics, that matter could not be created or destroyed, and energy cannot be created or destroyed, and made energy, and fluctuated energy, or at least made a huge fluctuation in energy, and even created matter in the process. And I think that's really cool, that none of us can break that law. It's a fundamental law, and yet we all have to acknowledge at some point it was broken by something or someone. And I'll leave you there. But as far as the assignments go for this week, I'll post, if not posted, they'll be posted soon for class time. You'll see them on RunWeb. That's where you're gonna do them on class time. The assessment this week is something pretty. I hope it's simple enough. I'd like you to do the same thing that I've done a little bit. Just find some examples of kinetic energy turning into potential energy, and potential energy turning into kinetic energy, and write a one-page paper on that. So I want at least maybe at least 3 examples, at least a one-page paper, and inside that paper, maybe at least make sure that one of your examples demonstrates how that thing about velocity, or if you have more velocity, you have more kinetic energy, or if you have more mass, you have more kinetic energy. How that increases your momentum. Okay, and we'll use Turnitin to turn those in. So, thanks you all. I had a lot of fun with this. Thanks for watching this with me. Feel free to contact me personally. We can walk through more of this together. And if not, I'll see you soon.